Yeah, be great.
Okay, so we are recording now. We've got our U substitution rules, and just kind of briefly mention that, well, we want to reverse engineer the chain rule and the product and quotient rules that we know from Calc 1. And our idea is, well, if I'm taking a derivative of a composition of functions, this is our well-known chain rule that we got. And if we want to do this in reverse, well, what we want to do is be able to recognize a composition of functions, and in particular recognize kind of what is the inside function, and to be able to recognize that the derivative of that inside function also appears under the integrand, right? Because what's going to happen is, well, if I just integrate both of these, essentially what we see, well, we know from the fundamental theorem of calculus that the integral of a derivative essentially the integral undoes the operation of a derivative, and we are simply going to get that f composed g of x is equal to the integral of f prime g of x times g prime of x. And I'm going to put my dx there specifically. So the differentials are going to be very, very important for this. I don't know how much your Calc 1 teacher emphasized it. I'm going to emphasize it a lot for these first couple of days. So we want to recognize.
You're off screen a little bit.
Thank you. Let me see. So I may have to move the camera here. Maybe I'll just pull it up. Can you guys still see that? It's not too small.
Yes, I see.
Pretty good, pretty good.
Cool. So that'll give me a little bit more space to write. I think the camera can pick up more of the page then. So we want to recognize integrals of this form. And then as well, know how to solve them. I want to put a little emphasis here on the dx is important, because what we're going to do is use a substitution. So let's get a new page here. Let's see an example. Let's just suppose we want to integrate a function like, let me pull up my examples. One plus 2x quantity squared dx. So this one you guys should know how to do at the moment, right? What would our technique be if we needed to solve this integral? Well,
U substitution?
Well, yeah, U sub is what we're doing today. If we didn't know U subs, the only thing we could do is to expand that out. So we could square everything out, FOIL things out, and integrate. Okay, but let's change it a little bit. Squaring things out isn't too difficult. What if I actually give you something like this? We don't want to do that now, right? We don't want to do algebra to simplify our problem because it's a pain in the butt, right? We don't want to take something and raise it to the 5th power and FOIL it out 5 times. It's going to take way too long and almost not even worth it. So what we want to do is to be able to recognize an inside function and its derivative. So let me actually adjust the problem real quick. So let's do this. Let me do this in such a way that it's kind of a little more natural and easier to start off with. Let's start it with 1 plus just x to the 5th dx. So maybe not too difficult to raise to the 5th, but still, we don't want to do something like this to the 5th. So what we want to recognize is this guy here is a composition of functions. Namely, if I write this as something like f of x is x to the 5th and g of x is 1 plus x, then really what we have is f composed g. And that is what our function is there. And so what you want to be able to do is start recognizing what is the inside function. Our inside function was this guy. And to note that if I take a derivative of g, well, what do we just get? We just get 1. And so what do we want to recognize in the problem is that this inside function here and this guy match. So this is our essentially 1 dx. And so kind of what we want to think about is that, well, g prime of x is 1. We can also kind of think about it as 1 dx. And what we want to do is now make a substitution for that inside function. So what we're going to say is we're going to let u, as our common letter that we use for our substitution, is going to be 1 plus x. And then when I take a derivative, we'll have du is equal to dx. So what did I do there? Let's write it out in a different way, equivalently. I could have just had u is 1 plus x. If I take a derivative of both sides, let's say if I consider u as a function of x, this is just saying du dx is equal to 1. And so how do I get this statement here involving the differentials? We're really just taking these first order differentials. Everyone should be familiar with what du dx is. It is just the rate of change of u with the respect to the rate of change of x. And I can kind of treat these as variables in and of themselves. So if I just multiply the dx over, we get this statement here. So this is going to be our substitution. And this is why the differentials are very important in these situations, because the differential tells me what is the variable that we are integrating with respect to. If this dx is dx, then that says all of the variables in the function need to be x. I have to have them all x. We can't have u's and dx's together. It won't work. We'll get an incorrect answer, and it's not how the problem is ended up being solved. So let's plug these things in. So if u is 1 plus x, our integral now becomes we had 1 plus x to the 5th. Well, that 1 plus x is just u, still raised to the 5th power. And now my dx is just du. So we're substituting out both the variables in the function as well as the differentials. And this is an easy function to integrate now. What is the antiderivative? We just raise the power and then divide by the power. So I like to keep the constants out front, so I just write it as 1/6 u to the 6th, and then we have our constant of integration still hanging out there. So since this was just an indefinite integral, we started with x's. If we start with x's, means we need to end with x's for an indefinite integral. So I have my u's here. Now what do we need to do? We just need to back substitute. So our u's were 1 plus x raised to the 6th power plus c. And this is our solution. And just for posterity, we can check. If I take a derivative of what we just found, we should get back to the integrand of what our original problem was. And so here's what we will see. We will see the chain rule a little bit here in reverse. So if I take a derivative of this, the constant stays out front. I will bring down the power. You guys still seeing that? Now let me move it up. And then we will have our 1 plus x. We will lower the power. Our product rule, excuse me, our chain rule says that, well, now I need to multiply by the derivative of the inside function, which is just 1. And then that c goes to 0. And of course, what do we get? We get just back to our 1 plus x to the 5th. So back to the integrand that we were originally trying to work with. Does everyone see that?
Yeah.
Good. So I can't hear you guys. It sounds, let me check my sound real quick. Ah, that's why. Let me see. Microphone. All right, is that better? Someone say something.
Hello.
No, I still can't hear you guys. I'll give you camera USB ear. Let's see.
Your sounds like pretty far away.
Let me check my microphone. Oh, that was my microphone here. Let me change that. That better? Speaker should be good, and same as system. Okay, maybe I just need my headphones in. Okay, so let's do some harder examples. And let's see how things are going to work out. So we've got the integral of 2x square root of 1 plus x squared dx. So again, what are we looking for here? We're looking for composition of functions. We're looking for this like inside function as well as its derivative. And if you kind of look at the sheet, let's see where I just kind of pulled up. Let me keep my pages organized here. Right, the inside function appears, it should appear 1 on the inside, but then its derivative will appear on the outside and should be multiplied on the outside. So that's really what we're going to be looking for. And so if we look at this guy, you kind of see that, well, I have a square root going on, but then I have this polynomial as my inside function. And then this guy is the derivative. You should be able to kind of start to think ahead a little bit and have a little bit of foresight that if I take a derivative of 1 plus x squared, the derivative is 2x. And so this is how we want to make our substitution. We want to say our u is 1 plus x squared. Then when I take a derivative of both sides, we will get du is 2x dx. And it's this derivative, this 2x dx, that we kind of want to stick together. If we wanted to rewrite the problem, we can kind of put the 2x dx together. So we have these two kind of substitutions going on. So now when I substitute, we're going to have square root of the 1 plus x squared is just u. And then this whole thing, this 2x dx, is just du. The antiderivative of this guy, so hopefully you guys are pretty good at these now, or at least with the basics of polynomials and all the other functions that we start with, our trig, our logs, our exponents. And our square root is just u to the 1/2. And so when I antiderive, we are going to add 1. So 1/2 plus 1 will give me u to the 3/2. We want to divide by 3/2 is the same as multiplying by 2/3 out front. And then plus our constant. We started with x's, so we need to end with x's. So let's go ahead and back substitute. We've got 2/3 times 1 plus x squared to the 3/2, and then plus c. As a check, if we take a derivative of that guy, we'll get 2/3 times 3/2. We'll have 1 plus x squared. We'll lower the power, so that'll go down to 1/2. And then our chain rule says I need to multiply by the inside, the derivative of the inside, so we'll have times a 2x. And of course, that gets us right back to where we started. Any questions? Okay, so more examples. Let's see some of the more complicated ones. Some of the ones I want you guys to just practice on your own. Some of the ones that are a little bit easier. So these are just some of the problems I was thinking about doing. But I don't want to spend the time since we've only got 20 minutes. I want to see some harder examples. Maybe do that one here at the end. Exponential functions, sine functions. We've got exponentials and trig. These guys are pretty easy. So e to the 5x. Anytime there's just a constant, my inside function is 5x. So you may want to look to do that as a substitution. There is one point to address there, so maybe I'll do one of those guys for you here. Because sometimes the differentials don't work out. So, right, there's two substitutions going on really here. There's the substitution for the function, as well as these substitutions for the differentials. And we saw in this last one, it worked out really nicely. The differential du, it was just 2x dx, and it was very nice because there was a 2x dx in the problem. It doesn't always work out that nicely, but it doesn't have to be perfect in order to get it to work out. So just to note, the differentials it needs to match only up to a constant. So what do I mean by that? Well, let's take a look at something that's fairly easy. Let's say we have this e to the 5x dx, and we want to anti-differentiate this guy. So our inside function, well, I'm taking the exponential of 5x. So my 5x is on the inside. Our natural guess then is say, well, let's make our u 5x. But what does this mean? This says that du is 5 dx. So there's a little bit of a problem because there's not a 5 dx here, and there's not a 5 anywhere sort of written in the problem statement. But there's a du and dx, and they're related. They're equal up to multiplication by a constant. So that's what I mean. They need to match up to a constant. So since this dx is over here isn't 5 dx, that constant 5 we can just manipulate a little bit to get things to work out for us. One common thing we can do is to take this statement, our differential statement that we get, and to just multiply or divide things by constants. So I can really write this as, well, 1/5 du is equal to dx. And this is a common technique. Is to solve for dx. Because there's always a dx in the problem since we started with dx. So now we can just make that substitution. The thing to be careful about when doing this is to make sure that we're only manipulating constants. You can use it for manipulating functions. You just have to sort of adhere to one of the first comments I said, that whatever the differential is has to match all the variables in the function. So since we're changing our differential to u's, du's, all of the variables in the function need to be u's after that. So we'll go ahead and make our substitution. We'll have e to the 5x is just u now, and this dx is 1/5 du. And you can think of all of these as just being multiplied together. So since I'm just multiplying by a constant, we can bring that all the way out front, and we've got e to the u du. And then integrating that, pretty easy. Just goes e to the u plus a constant. We started with x's, so we got to end with x's. And so we'll have 5x plus c. So I'll leave it to you guys to check that one. Let's see some more examples. So we've got about 15 minutes. We're running a little bit behind. Unfortunately, that's the way the schedule goes. When I saw the schedule, we do gotta hit the ground running, but it's hard to hit the ground running when we do gotta address the all the first day crap, you know. Always gotta spend time talking about the syllabus, the quizzes, and all that. Let me see. So let me pick out a good example. We want to talk about, well, now what happens when I have definite integrals? So of course, definite integrals weren't that much harder than indefinite integrals, right? The real work is doing the actual integration, finding the tricks to do the integration. Then, well, you just got to plug in some numbers. And in this case, there's just a little bit more work to do. So let's do something like, let's see. Let's do one that's not too terrible. Let's do this guy. Let's say the integral of 1 to e natural log of x over x dx. So this one can be a little tricky because there's not really a nested function. There's not this composition of functions. Really, the only function involved is natural log of x and x. So natural log of x is kind of a pain. It's actually one of the harder ones to integrate. We actually we're not going to be able to integrate it until tomorrow, until once we start integration by parts. So anytime we need to integrate a natural log at the moment, you should look for, well, what is the derivative of natural log? And the derivative of natural log is 1 over x. So we're going to rewrite this as it's actually, all right, let me write it this way in order. So I'm going to say natural log of x times 1 over x dx. And we've still got our bounds of integration. So the way we want to deal with this is, well, since the derivative of natural log of x is 1 over x, I just want to make this guy as my u. So we're going to have u is equal to natural log of x. Du is then my 1 over x dx. We make our substitution, and my problem becomes u, and then this 1 over x times dx is now just du. Okay, so far so good. I have a du. All of my variables are in terms of u, but we need to be careful. These two bounds are x values. So we need to change them. And there's two ways to do this. This is the first way. This is the way I kind of like to do it. It's usually, for me, it's a little bit quicker. We cannot reuse these same bounds because, again, this dx says everything involves x, which means these numbers are values of x. And now that we've changed the variables, we need the same corresponding values of u. So how do we solve those? We can essentially just go back to our substitution. And we can plug in the x values. Can you guys see that? To find the u values. So I'm going to be running out a little bit of space here, but I can rewrite things on the next page if we need to. So what do we want to do is, well, u is equal to natural log of e. So this is just the upper bound. For x. And so what do we get? What's the natural log of e? Just 1. And likewise, we get u is natural log of 1. And that's going to give me 0. So we plug in the upper bound for x into our substitution. That'll give me the upper bound for u. Plug in the lower bound for x. Give me the lower bound for u. So what does our integral become? Let's see, maybe I can write it split page. So we had this u du. go.
You're a little bit off. There you go.
Let's see. So we had our u du, and then what are our bounds? Well, the upper bound now is just 1, and the lower bound is 0. And u du, that's an easy integral. That's just going to go to 1/2 u squared. We don't need a plus a constant because we've got a definite integral, and my bounds are 0 to 1. We evaluate. So we'll get 1/2 times 1 minus 1/2 times 0, and we just get 1/2 for that guy. So that's how you deal with definite integrals. So not much more to that. You just got to have an extra step of remembering, hey, I need to change my bounds. And actually, you know what? You don't even need to do that if you don't want to. So let's do the other method. The other method is, well, it had this integral of u du. If you don't want to go through the process of finding the bounds, let's just not even worry about this. So you can either draw some circles there. Remember that you do need to evaluate it, or you can, write it as like u top and u bottom. Because the numbers aren't terribly important at the moment. We really just want to find the antiderivative. That's what our trick for this U substitution was really helping us with. So when I find the antiderivative, again, we just have this 1/2 u squared, and I still need to evaluate it. But let's say I skipped that step. I didn't check the bounds because I didn't want to worry about it. So I'm just going to put something there. That I probably shouldn't draw circles because those look like zeros, but I know that I just need to evaluate. Let's put bullets there. Those are going to be our empty bullets. Well, okay, that's my antiderivative. Well, how did we do the previous problems? Everything started in x, so let's go back to x's. So if I want to go back to x's, we had 1/2. Our substitution, remember, was natural log of x. So I've got 1/2 natural log of x. I'm going back to x's now. I still need to evaluate, but now that I'm back in x's, we can just plug in our bounds for x. And the original bounds we started with were 1 to e. So we can just keep using those. We're back in x's. We're back to our x bounds. You don't even have to worry about finding the other ones. You did just kind of have to do this extra step of rewriting the back substitution. And now remember, when we plug it in, we're essentially doing the work we did finding the u bounds, just now we're doing it here because we still got to plug in those bounds to natural log of x. So we will have natural log of e minus 1/2 natural log of 1. And then, of course, we get the same thing. So natural log of e is 1. Natural log of 1 was 0. Any questions on that?
Sorry, quick question. So if it ended up being u squared when you plug back in, like for the original x values, does it have to be the natural log of x squared, or does that not?
Yes, thank you for that. So yeah, looks like I just missed that mistake here. So natural log of x squared, natural log of e squared, and squared there. And actually, it looks like I forgot the squareds over here. Of course, luckily, the numbers were nice enough that those squareds didn't matter. Yeah, thank you for catching that for me.
Thank you.
Yep. Any other questions? Okay, so might have to start with this again tomorrow. One thing I do recommend you guys looking at is the activities for the day. So we don't have time since we only have 5 minutes. Let me share my desktop here. The key part of this is recognizing those substitutions. That's the hardest step. Hopefully you guys are pretty solid with understanding the antiderivatives. And so the key step is, well, if I can get it into a format where I can recognize an antiderivative, then I can do the antiderivative. So take a look at the activities for today. So that was the antiderivative review. This practicing the mechanics of U substitution. So they can get a lot more complicated. And really the key thing is to set up the integral. So they say to evaluate, so go ahead and find the antiderivatives if you want. But the other activity for today, so if you look on the schedule, we've got 2 here, is this guy. And a lot of it just says, make the substitution and simplify, but do not evaluate, which is really like we're just telling you, focus on the key steps to making a good substitution and being able to find an antiderivative. So practice a lot of these guys. So like, what do we have? We've got x times sine of x squared. What is our inside function? X squared. And if I make u is equal to x squared, my du is going to be 2x dx. And since I have that x dx, that substitution should work out nicely, but maybe we got to then manipulate the 2. So practice some of those. I will say some of the trickier ones can be the square roots. Sometimes when you make substitutions for square roots, can be a little tricky. Likewise, there are things called linear substitutions. So we only got a couple minutes. I did want to talk about those. It's a little complicated, so maybe we'll check those tomorrow. And let me look over my examples. Any other key ones that we might want to look at? I don't think so. I think it'll be a little hard to get to today. So we'll try to just pick up with that kind of stuff tomorrow. All right, so that's it for today. Let's talk about office hours. So they want me to have like a couple office hours a week, which are going to be a little weird to have, especially since we're digital. Let me know either through email or if you want to just drop a comment or anything like that, what good times for office hours are going to be. For me, it might almost be after class on certain days or even before class on certain days. Since we don't have consistent quizzes, it's a little weird. I always like to have my office hours like the day before a quiz to make sure I'm available, but since our quizzes aren't consistent, that may not be good to have set office hours. So I can always be flexible with my office hours if you guys need them. Let's see, anything else this video? So I think I'm still recording. I'll go ahead and stop recording since we're stopped lecturing. I'll put the videos online and try to get these up on either Canvas or Google Drive.